So basically, suppose F is a field. Then, so let's define finite field extensions recursively. So the say alpha is in another field K. Uh, so the way you define f of alpha is P upon Q alpha, where P and Q are polynomials in f of x. And so this is f alpha. And now similarly, if you want to define f of alpha comma beta, you repeat the same process, and now you replace f, the what we did for f of alpha. So you replace f by f alpha, and basically it's like so this will so this is basically p of beta upon q of beta, where p and uh, p and q are in f of alpha comma b. And you can keep on repeating this process, and you can get f of alpha 1, alpha 2, so on till alpha n. And you can also extend this to infinite extensions in the same way. So what we focus on is just finite field extensions, which means the alpha i's, the number of alpha i's here is finite. So this is finite.
Yeah.
Um, so now basically suppose suppose f is a field, and say you have that k upon f is a field finite field extension. So we define what is called the Galois group of f upon k. This is called gal f upon k. So the way this is defined, so yeah. Oh, sorry. Yeah. So the way this is defined is is basically the set of okay. I'll define automorphisms of a field in just a moment. So basically, the set of automorphisms. So sigma in morphism f upon k, such that sigma fixes k. So what are automorphisms?
K, right? You
So
wrote as.
my bad. Yes, thank you. And the way you define automorphisms is basically Oh my God, there's a mutation. So the automorphisms are just so field homomorphisms. So basically maps F to F, and these are injective field homomorphisms. What does that mean? So it means sigma AB is sigma A times sigma B, and sigma A plus B equals sigma A plus sigma B, and the identity is preserved. So this is what automorphisms mean. So let's take some examples. So for example, if we take K as Q and say F as Qi, so the basically the automorphisms so you're looking at the automorphisms. So the only automorphisms will be the ones which send I to I and 1 to 1 and 1 to 1, and the automorphism that sends I to minus I and 1 to 1. So does everybody see why the second automorphism also preserves Q?
Yes.
Okay, sure. So basically we see that so this is sigma 1. Oops. So it just consists of two automorphisms, sigma 1 and sigma 2. And similarly, you can do the others. And now the main theorem that we will be using is the fundamental theorem of Galois theory. So, for this, we first need a terminology. So let uh, K upon F be a finite field extension. So G is again K upon F, and say H is a subgroup of G. Then we define the fixed field of G uh, to be the set of elements in K which are fixed by so such that sigma A equals A for every sigma in it. Um, yeah, so, so this is fine. And Yeah. Now, what does the theorem say? So basically, again, let G equals K upon F H subgroup of G. Uh, so, so the fix uh, so the fix uh, so, my bad. So the Galois group of K upon a fixed field of H is H, and so similarly, if E is the set of subfields of K, then fixed field of G on uh, so does everybody see this? Yeah. So this is what the fundamental theorem says.
Can you go to the previous slide once?
Uh, oh, sorry. I cleared that slide. So,
Oh, okay.
did you have any doubt in that?
What was Galva again? GAL.
So do you understand what the automorphism group is?
Yes.
So the basically Galois K upon F uh, is the set of automorphisms sigma in um, odd K um, that fixes F. So sigma fixes F.
Ah, okay.
Yep. And so this is the fundamental theorem of Galois theory. So which I'm not going to prove. Um, and so from this corollary follows, which we will be using. So basically, we have that say H1 is a subgroup of H2, which is a subgroup of gal k upon q, and say f1 is gal h, sorry, my bad. So f1 is the fixed field of gal k upon q upon h1, and similarly define f2. Then we have that so we have that f1 is yeah, so we have that f1, f2 is a subfield of f1, and can be shown that f1 to f2, f2 to f1 is equal to h1 to h2. Okay, so this will become clear from the diagram. Um, uh, does everybody understand what the theorem says?
Not really.
Okay. Okay, let's take an example. So basically, say uh, say we have k equals q root 2 root 3, and f is q. So gal k upon f, want to find this. So this will have degree 4, and it's basically the elements are, so one element is identity, uh, sigma 2 is, so get root 2 gets sent to root 2, and root root 3 gets sent to minus root 3. Sigma 3 is root 2 gets sent to minus root 2, root 3 gets sent to uh, root 3, and sigma 4 is root 2 gets sent to minus root 2, root 3 gets sent to minus root 3. So say you define automorphisms by defining the basis elements like this. So sigma 1, sigma 2, sigma 3, and sigma 4. So we get that gal k upon f will be
How do you show that there are no other automorphisms?
okay. So basically, you can just check since this is a Galois group. So first you have to see that k upon f is Galois. So why is that? Why is that true? Because so first let's look at k upon f. So degree of k upon f. So by tower, we see that this is,
4.
yeah, this is 4.
Yeah.
And so and now you can see that k upon f is also, so k upon f is the splitting field extension. So the splitting field extension for x square minus 2 times x square minus 3. right? Because the roots, the things here are root 2 and root 3. So these are roots of x square minus 2, x square minus 3. And then you can see that this polynomial is separable, so it does not have any repeating roots. And so you'll get that k upon f is a Galois extension. And so for Galois extension, you have that this size, uh, and now basically you can note here that each of sigma 1, sigma 2, sigma 3, sigma 4. So each of these are fixed q, and so the size of this is at least 4. But this is always a subgroup of the set of automorphisms, which is also 4. So basically, in this case, you have that.
Why is the set of automorphisms 4? That is what the question was, right?
Yeah, right. So this is the reason, right? Like the automorphisms basically are determined by the action on the roots, right?
Because they all fix q, and so only like where root 2 and root 3 get mapped to
Like they're
this.
fixed by what happens to the
Yes.
by root 2 and root.
Yeah, I got that, but why not any other automorphism? That's what I did not get.
No, like because you showed that these are 4 automorphisms and it can be at most 4. So these are the only 4.
Why is it at most 4?
Because like root 2 and root 3, where they map to, I guess that only determines. Uh,
I don't
Uh,
get it.
okay, like we also have this, right? Does this make sense? And we have shown here that k upon f is 4. Hello. Sorry, Yash. Is this part fine? Should I move on?
yes.
Okay. Um, So okay. Yep. So we determine gal k upon f.
Sorry, I got this.
Oh, to be sigma 1, sigma 2, sigma 3, and sigma 4, right? And now suppose you take some subgroup of this. Say you take sigma 1 comma sigma 2. So remember that sigma 2 was the one that sent root 2 to root 2 and root 3 to minus root 3. So if you look at so the fixed field, So if you look at fixed field G upon H, uh, G is Gal. Yeah, so G upon H is basically the fixed field of sigma 3, sigma 4.
What
So
is the fixed field? It is like,
okay, so the fixed field of some subgroup H of the Galois group. Sorry. So this is basically the set of automorphisms that such that every element in that subfield is fixed by the elements in it. So for example, in this case, if we want to look at the fixed field of sigma 1, sigma 2, so we want to find the subfield that is fixed by the automorphism sigma 1 and sigma 2. So sigma 1 is just identity, so everything is fixed. So what we want to see is the things that are fixed by sigma 2. So that will be exactly q root 2, right?
Yeah,
Because
like you are,
yeah.
yeah, okay, I got it.
And so now we are looking at fixed field G upon H. So that is fixed field sigma 3, sigma 4. Sorry. Oh, oh, my bad. This is sigma 1, sigma 3. So, and sigma 3 send root 2 to minus root 2 and root 3 to root 3. So this is exactly q root 3. And then, so if you apply the theorem, what the theorem tells you is that you should have that. So q root 3 is a subfield of so okay, if we take this as h1 and say we take h2 as sigma 1, so the fixed field of this is just so it's just the entire field. Entire. Oh, my bad. So it's the entire field K. And moreover, it tells us that this degree q root 2 is root 3 is to q root 3 should be same as the index of the groups in the inverse direction. So that is sigma 1, sigma 2. So everybody agrees with this, right?
yes. Could you like once show the general statement, which I forgot?
Oh, okay, sure. Just clear this.
I think it's better to use some whiteboard because it keeps getting cleared and then we can't
Oh, actually,
look back.
I'm using a whiteboard only, but oh, I thought there's just a limited space. Uh, Either way, so like I'll send you the notes after this thing. So
Okay. Do you have another lecture on this?
sorry.
Do you have another lecture on this?
Another lecture
I
on.
guess you meant will it be like a series, one more lecture?
Oh, I think I have another one tomorrow. Yeah.
Oh, okay.
Okay. So basically, the statement was, so if G is the Galois group of K upon F. And, so H is in G. Okay. Then the Galois group of G upon fixed field of H. So this is exactly H. And similarly, if so, so this is a subfield of K. Then the fixed field. Oh my God, this should have been K. And the fixed field of G upon so this is exactly so this is what the statement says.
Could you like also for once like explain all the notation in terms of automorph, like what they represent in terms of automorphisms?
Yeah, it's very hard to parse them all
Like,
the time.
like yeah, gal of K like slash fix of H, does that represent automorphisms that fix H and then looking at what other elements of K, or sorry, like let me repeat that.
So what the
I
fix of
understood it in the
H?
previous example, but like could you tell it in terms of automorphisms what each of these represent
Okay,
or
yeah.
fixes
Uh,
basically?
so basically, what this is saying is that the Galois group of K upon fix X. So this means the set of elements in the sub. Oh my bad. So this means that the set of elements in G which fix every element of K upon fix H is exactly H. So what I mean by this is basically like yeah, like so what this means is like the set of uh the set of elements in G um so which fix every element of okay, like fix H is the set of elements that are fixed by everything in H, right?
Yeah, like yeah.
And so K upon fix H are are the things. Oh, sorry. Oh, there should be a G upon H. My bad. So um, um, yeah. Okay. Yeah. So yeah, so what K upon fixed H represents is the set of cosets. So um say the elements fixed by H are like so basically it forms cosets like this. So A1, A1, A2, so on. So where AIs are the elements which are fixed by everything in H, and K upon fixed H are just the set of cosets. And now you're looking at gal of this thing, and what it's saying is that the elements in G which fix all these things is exactly H.
Yeah.
Okay, I guess I should maybe I'll give an example with the previous one. So we had gal k upon f is sigma 1, sigma 2, sigma 3, sigma 4. And so if you take H as sigma 1, sigma 2, then what so then this becomes gal of q root 2 root 3 upon, and fix H is just q root 3. So how can you, so what you're doing is you're considering the maps of root 2 root 3 which fix everything in q root 3. So basically you're just going to send root 2 to minus root 2, and
So the automorphisms that will fix Q root 3.
yeah, exactly.
Okay.
So that will be just sigma 1 and sigma 2.
Yeah, so basically, in general, that means we consider like a set H of automorphisms, which is a subset of G, and then we look at the like what we can say subfields, I guess, fixed, which are fixed by H, and then we
Okay, yeah.
yeah, and then we look at all those automorphisms which also fix those things which were previously fixed by H.
Yeah.
So that is obvious that why should it be like H only? Right?
Yeah. 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 So this is the main thing, and then okay. So now I guess I'll move on to the okay. So cyclotomic field extensions. So sigma n is cis 2 pi by n, and I'll call the cyclotomic polynomial or the minimal polynomial of this phi n x. And okay. So now let us look at an application of this. So okay, let's consider constructibility of regular n-nots. So now the tools that are allowed are ruler, compass, and the second tool is angle bisector. Has anyone heard of this problem before?
Yes.
Okay. So do you know what the answer is?
Was it something like 7? I don't remember.
Okay. So the conjecture is that the only regular n-gons which are constructible using this are the ones is that phi n is a power of 2. And
Phi
now,
n like the totient.
yeah, okay, this is the totient function.
Okay.
Okay, so where does the phi n come from? So the motivation is basically that, remember that
Size of a group, maybe.
yeah, essentially. So So we have that the basically the degree of the minimal polynomial of
Yeah, that is
alpha
phi.
psi, that's phi n.
Yeah.
And so essentially what we want to say is that this degree being a power of 2 is a necessary and sufficient condition. So let's look at what things are actually constructible. So first of all integers are obviously constructible. Um, okay. Now suppose n is a natural number. So does anyone see why 1 upon n is also constructible?
Wait, what are we trying to construct? Not regular polygons?
Yeah, basically now what you're trying to do is you're trying to classify uh, all the constructible things. Uh,
Can you go to the previous slide, Mars?
sure. Oh, sorry, previous slide. Okay. I just no, so we are looking at this. So we are looking at constructibility of regular n-gons. Okay, maybe yeah. So the idea is that regular n-gons are constructible if and only if zeta n is constructible.
Yeah.
Yeah. So yeah, everybody sees why this is true.
Yeah.
Okay. So now the idea is to basically, so we want to somehow use the fact that so this we want to somehow use this thing. So what we want to do is we want to classify the set of all constructible things. So okay, so the first conjecture is that Q is constructible. Um,
What tools were we allowed? Could you repeat once? Yes.
Yeah. So we have a ruler, compass, and an angle bisector.
Yeah.
So the ruler only has a unit measure. So you can just mark a unit measure on the ruler. And angle bisector can be used to bisect two given lines, the angle between two given lines. Okay. So does everybody follow till here?
Yes.
Okay. Can I clear this? Okay. This,
Mhm.
So okay. So the now we want to show that everything in Q is constructible. So now clearly, like suppose R is constructible, then we have that NR is also constructible, right? Where N is in Z, because you can just keep on repeating the process N times.
Yeah.
So that's why the idea is basically if we can show that 1 upon N is constructible, then that means Q is constructible. Where N is in the natural numbers. Okay, this is fine, right?
Yes.
Okay, so so basically the idea to show 1 upon N is constructible is you consider the origin 0, 0. Consider the point N, 0, the point 0, 1, 0, -1, and now you consider this. So consider this triangle. So this consists. So this triangle consists of constructible points, and so you can construct the circumcenter of this triangle as well, right?
Yes.
Okay.
Like
So
perpendicular bisectors can be drawn.
yeah, and so what you do is you consider the intersection of the circumcircle. Okay, assume this is a circle. So with the x-axis, and say this point is P, and now by so this distance is N, and say this distance is X. This
Okay,
is
yeah, I see. Like part of a point
so
gives.
this yeah. So this distance is
Yeah.
1 upon N.
Yeah. Nice.
So 1 upon N is constructible as well. And so we have shown that Q is constructible. And now, the next step is to basically find so necessary so let's find a necessary condition for alpha in C to be constructible. And basically the idea is that the necessary condition is that Q alpha is to Q should be a power of 2. So why is this true? So basically the way we have defined constructibility. So if alpha is constructible, this that means there is a sequence. There's a sequence of steps in the construction of alpha. So suppose the points at those construction steps were alpha 0, then alpha 1, then alpha 2, and so on till alpha k. Now the idea is that at each construction step, so alpha 0 is in Q. Now the idea is that at each step, we must have that Q alpha I plus 1 is to Q alpha I is either 1 or 2. So to prove this, so do we see why it just suffices to show that Q alpha 1 is to Q is 1 or 2? So that is, it just suffices to show this thing for the first step. Is that fine with everybody?
Can you repeat a bit this slide?
So basically, we are considering a sequence of these steps. And what I'm saying is, I want to show this thing, and I'm saying that it is sufficient only to show this. That is the same thing. Same thing will keep on happening for the following steps.
Okay. It's a power of 2. Yeah.
Okay. So why is this true? So now we only have three constructions. So ruler, compass, and so angle bisector. Okay. Okay. Now the idea is, so if it's just a if it's just a ruler construction from Q to Q alpha 1, so like for alpha 1, then what that means is that alpha 1 is in Q, because with a ruler you just have linear
Yes, yes.
transformations.
Mm.
And now this can I okay, just clear this. Now the second option is you can have a combination of ruler and oops, sorry. So you can have a combination of ruler and compass. So this will be an intersection of a line and a circle. Now, by translation, I can assume that the circle is the unit circle. Is this fine?
Yes.
So then suppose Z is, so we are constructing alpha, and so suppose the points on the lines were Z1 and Z2. Then basically we want to solve for mod
So
alpha.
basically, like, would it be something that you'll get a intersection and a line and circle intersection? So it will be a complex number at most, and that is a degree 2 algebraic.
Yeah, and that will be the root of something which is
Yes. Yes.
because you have, so the
Hmm.
equation of line is something like alpha minus Z1, alpha minus Z2, oops, upon Z1 minus Z2 is say T. And then you just you take mod on both sides. Like basically you have something like alpha is T Z1 plus 1 minus T Z2. So if you take conjugates on both sides, you get alpha conjugate is T is real, so it will just remain like this. Z1 conjugate plus 1 minus T and Z2 conjugate. And so when you multiply these two, this will be 1 is P of T, uh, where this has degree at most 2. So this is a quadratic in T. So when you solving for alpha just means solving for T. And so T is a root of a quadratic. So that means alpha is also a root of a quadratic. And so this will have degree 1 or 2.
Yeah, yeah, we get it.
And similarly, you can do the case of circle intersection circle. Um, and so for angle bisector, again the same thing, because so say again you can translate one of the points to origin, and it is like you're bisecting the angle between Z1 and Z2, and alpha is here. So By scaling again, I can assume z1. Z1 and Z2 are things on the unit circle. Uh, my bad. So by scaling again, I can assume that alpha is on the unit circle, and then I'll have something like um. So alpha is Z1 e raised to I theta, and Z2 is alpha e raised to I theta. And so you just substitute, and basically you get so if this is the complex number set t, so you get z2 is z1 t squared. So again a quadratic, and
Hmm.
so alpha is also a root of a quadratic, and so you can do this similarly. So essentially what we have proved now is,
So we have the necessity part, right?
yeah, so we have proved the necessity. And so if we assume that the regular n-gon is constructible, that means zeta n is constructible. Um, so zeta n is constructible, and so we have that q zeta n is to q is powerful, and so phi n is a powerful. So we've proved the necessary. Now let's show that this is actually sufficient. So sufficient. So does everybody see why it suffices to prove for prime powers?
Yes, I think.
Okay, so basically, like if you have so if you have a and b are coprime, and say sigma a and sigma b are constructible, so by Bezout's there is x and y, so is that ax plus by equals 1, and so basically you get sigma ab is sigma a raised to x and sigma b raised to y. This is fine, right?
Yeah.
Oh, yeah. And so now we just do it for primes. So say n is a prime, so you have p. Now the idea is that um, so gal q of zeta p. So so essentially you should have gal q of zeta p is to q is somorphic to z upon p minus 1. So does everybody follow this?
Could you like brief it? Math?
Oh, sure. So basically, the automorphism maps uh, are just so sigma n to sigma n raised to I, right? Because these are the roots of the polynomial. So the polynomial is just x raised to p so 1 upon x minus 1. So the automorphism maps are just these.
There are p minus 1
Oh
automorphism.
yeah.
Okay. So now in this case we have that p minus 1 is a power of 2, and uh
Oh, so basically this is the Fermat primes thing, right?
sorry.
Like the Fermat primes thing.
Yeah. Yeah.
Because like k also needs to power of 2 and that.
Yeah, this is where the Fermat primes comes from.
Oh wow. I'd only like seen about it in very philosophical lectures, but actually today I saw the math behind it.
So yeah, so basically yeah, we had p minus 1 is a power of 2, and now what we want to do is we want to show that this is constructible. So if we can, so basically if we can find a chain of fields q in f1 in f2 uh, so on till f. Okay. So this is f0. So the idea is that you can find a chain of fields such that this happens where this degree is exactly 2. So I'll get back to this in a moment. Now let's see why this would be nice. Oh, my bad. So essentially what happens is suppose you have that uh, uh, k and f are fields such that k is to f is equal to 2, and everything in f is constructible. Then I claim that everything in k is also constructible. So can anyone see why this is true? So basically, like the idea is something like when you have that k is to f is 2, you can write k equals f of alpha for some alpha which has degree 2 over f. And then if you can do something like this, then so alpha will be root of a quadratic, and then you can just construct alpha um, by by just taking a square. Like okay, like for example, if you have something like root 2, for example. Excuse me. So so you can just so by Pythagoras you can just construct so 0 0 0 1 and 1 1, and and you've constructed root 2. Let's make a new slide. Okay, so my claim is, so if you have k is to f equals 2, and f is constructible, then k is constructible. So the proof of this is, so first, okay, is this part clear? Why this is true?
Yes, yes.
K is equal to f of alpha.
Mm-hmm.
Okay. Now, if we can show that alpha is constructible, we'll be done, right?
Yes.
So basically, you have something like alpha square plus a alpha plus beta equals 0. Um, and you want to show alpha is constructible. So uh, you do can you can rewrite this as alpha plus a by 2 square plus b minus a square upon 4 equals 0. So essentially, you just need to show that square root b minus a square upon 4 is constructible. So that is yeah. So oh, sorry, my bad. A square, but so we want to show this, and idea is okay. Now the idea is to use the angle bisector condition, right? So what, so, so, okay, so let's stay. Stay. So now let's consider equation comes to theta. So this is square theta minus 1. So anything of the form 2x square minus 1 minus um, 4. Oh, 3.
I guess maybe you should pause for a bit because they like the one who were recording, they have left.
Oh, okay. Oh,
I'm recording.
Oh, okay. Sorry.
my bad. Okay, sorry. My bad. Yeah. So basically, if you have that, so I can assume without loss of generality that alpha is again on the unit circle, and basically, what I want is so say alpha is cos theta plus I sin theta, and alpha square is cos 2 theta plus I sin 2 theta. And so what happens is you have that alpha square is constructible, and so these things are constructible, and so this is constructible, and this implies that alpha is constructible as well, because you can just bisect the angles. Um, yeah, sorry, my bad. um, okay, so what we proved is the following. So we proved that if k is to f equals 2, and f is constructible, that implies k is constructible. And now we had so now if we can show that there exists a sequence of subfields q in f1 and f2, so until fk, such that fi plus 1 is to fi equals to, then by this lemma, um, and the fact that q is constructible, so we'll be done. Okay, does everybody follow this much?
Yes.
Okay. So now we just need to prove this, and so this is where the fundamental theorem comes in. So basically just so consider G as gal K upon Q. Sorry, my bad. So now, so now this statement, so by fundamental theorem, so this is equivalent to finding a sequence of subgroups. So this is that. So this is equivalent to finding a sequence of subgroups. So, with one. So this is just the identity, and G1, G2, so on till GK, and this is equal to G. So does everybody see the correspondence between these two things? Oh my God, I forgot. Gi plus 1 is to Gi equals to. So, the page. So what I'm saying is finding a sequence of subfields Q in F1, in F2, Fk is, so this is equivalent to finding a sequence of subgroups. Uh, the identity is a subgroup of G1, so subgroup of G2, subgroup of GK. So is this clear? Because I can just take Fi as the fixed, I can just take Fi as a fixed field of Gi. Does everybody follow this much? Hello.
Like, could you like just repeat from the previous page? I could not follow.
Oh, okay.
Like
So
where you like transition that equivalence between that and the.
okay. So basically, what I'm saying is that so finding a sequence of subfields Q and F1 till Fk, and so the to find a sequence of subfields Q F1 till Fk says that F
Yeah,
F
yeah, yeah, yeah.
sorry,
No, nothing.
says that Fi plus 1 is to Fi equals to. So this is equivalent to finding a sequence of subgroups of G. So this is just the identity automorphism, a subgroup of G1, which is a subgroup of G2, so until GK, which is G, such that Gi plus 1 is to gi is 2. Is this correspondence fine?
Like you can proceed. Right.
Okay. Sure. So then what we get is now we just need to show this part. And so the way you do that is, so you have that G is basically a cyclic group, right? Because it is generated by sigma 1, which sends zeta n to zeta n. Uh, which sends zeta n, so zeta n square. So everything here is generated by this isomorphism. And so this is very easy, right? Because G is basically a cyclic group. And the size of G is power of 2.
Mm.
Okay. Um, yeah. So is this fine?
Yes.
So yeah. So basically, since we have constructed such GIs, so by the correspondence, we have constructed such subfields FIs, and such that so Fi plus 1 is to Fi equals 2, and by the lemma, since Q is constructible, so by induction we get that Fk, which is same as Q zeta n, is also constructible, and thus zeta n is constructible as well. And so we are done.
Nice.
So moving on, now I'll talk about yep, talk about algebraic numbers and integers. Just give me one moment. So just give me. Yeah, I forgot to put my laptop in charge. Okay. So now I'd like to discuss algebraic uh, algebraic numbers and uh, integers. So algebraic numbers are just so I say alpha in C, then algebraic number. If and only if there exists f of x in zx, such that f of alpha equals 0. And now then algebraic integer is essentially just if f is monic as well, then I say alpha is an algebraic integer. Um, so here, here's a problem. So suppose D is square free and consider K is Q square root D. Then find the algebraic integers which belong in K. Okay. So yeah, let's try this for um, um, this is a motivating example. So I'll discuss this in 2 minutes. Okay. Does anybody know the answer?
Like I read about it previously, but I forgot it was based on like two cases, I guess. There were
Yeah,
based on the
yeah, that's right. So what you do is you consider D congruent to 104 and D congruent to 304. Um, okay. And so I'll not prove it, but so what we get is when D is 1 mod 4, then you can characterize all such numbers as z 1 plus square root d by 2. What does this represent? So this is basically the set. So p of alpha, where p is in zx and alpha is 1 plus root d upon 2. So in this case, it will just be n. So it will be of the form a plus b 1 plus root d upon 2. So every such thing. Okay. And then uh, and in the case d is 3 mod 4, this is easier. So you just get it will be z of root d. This is defined the same way. And so this basically motivates us to ask the question. So uh, say you have a field K, such that it is a finite extension of Q. So K upon Q is n and less than infinity. Then so what is OK? That is the uh, so that is the set of algebraic integers living in K. So alpha and OK, and alpha is an algebraic integer. So now we try to study what this looks like. And so let's look at the additive structure. Okay. Um, so the field, so I'll just introduce some terminology. So when when I have something like k is to q is n and less than infinity, I say k is an algebraic number field. And OK is known as the ring of integers of K. So why is it called ring? So that's what we're going to show. So our goal is now to show that OK is a ring. Um, so now first we explore a proposition. So alpha and C is an algebraic integer. Uh, if and only if so, so so if and only if z z alpha is basically finitely generated. Um, Finitely generated z. So what do I mean by this? So this is basically saying z alpha is of the form uh, a1z plus a2z, uh, so until anz. Um, Essentially, the equivalent way of saying this is basically that uh, so so alpha is a root. Okay, it's so root of f of x, which is mono, and degree f equals n. Um, and so this is also the same as saying z alpha to z equals n is finite. Okay, so this is basically what you are saying is this index. So we are looking at this index as an index of groups with addition. So I'll define some things in module theory in a while. So this will become more understandable. So let's get to that. So I suppose R is a ring. Then uh, then an R module. So um, I say M is an R module if uh, so for every M1, M2, and M and R and R, I have R M1 plus M2 equals R M1 plus R M2, where I'm considering a map. Um, so considering a map R cross M, uh, so, so I'm considering an operation R cross M to R with this property and the property R1 plus R2 times M is R1M plus R2M. Um, and finally, R1 R2M is R1 R2M. Okay, so let's take an example. So for example, when I say so say alpha and C, when I say Z alpha is a Z module. So here what I'm doing is I'm just taking normal multiplication. So I'm just taking set counts set alpha to set and taking normal multiplication. Um, okay. So can you guys see why these three axioms hold? Whereas if I have an integer a, so I have p alpha plus q alpha is a times p alpha plus a times q alpha. So this is fine.
Yeah.
Um, okay. Now we define the notion of finitely generated. So finitely so I say M in short FG. So I say M is a finitely generated R module. Uh, if and only if okay, so if and only if there exists A1 to AN in M So that M is A1 on plus A2 on plus AN on. This is fine, right? Um, okay, moving on. Um, so now let's see how this helps us. So proposition. So I say alpha in C is an algebraic integer. If and only if Z alpha is finitely generated Z module. Can everybody see why this should be true? So one direction is pretty easy. Um, so when alpha is an algebraic integer, this is very easy, because then you just have Z alpha is Z plus alpha Z plus alpha squared,
Yes, yes.
so on. And suppose you have that this is a finitely generated Z module, then what you have is uh, Z alpha is P1, so P1 alpha Z plus P2 alpha Z, uh, so on till Pn alpha Z. Now what you do is say capital N is the maximum degrees of the PIs. So we just consider the polynomial alpha raised to n plus 1. And so this is in Z alpha. So this should be a linear combination of these things. So we have that alpha raised to n plus 1 should be equal to some A1 P1 alpha, so until AN Pn alpha, where the AIs are integers. But now the thing is, the maximum degree here is m by definition, and so this term doesn't get cancelled out. And so I've obtained a monic polynomial of which alpha is a root.
Yes.
And so this means that alpha is an algebraic integer. Okay, so this is fine. Excuse me. Now let's see how this helps. So we wanted to show that the set of algebraic integers is a ring. We want to show that if alpha beta are algebraic integers, then alpha minus beta and alpha beta are also algebraic integers. So now what we do is, so we consider Z alpha, Z beta. So by our previous proposition, these are both finitely generated. And now if we can show that Z alpha minus beta and Z alpha beta are also finitely generated, then we are done. Right? This much is fine.
Yes, yes.
So now, so what we do is we try to consider Z alpha comma beta, right? So this is a natural choice because both alpha minus beta and alpha beta comma
Mhm.
this combination. And now since this is finite and this is finite, so this is finite as well.
Yes.
Because suppose the basis for A1, so A1, A2, AM is the basis for Z alpha, and B1, B2, Bn is the basis for Z beta. Then if we consider AI, Bj, so that becomes the basis for Z alpha comma B.
Yeah, makes sense.
Um, so we already have that Z, so Z alpha minus beta and Z alpha beta are subrings of Z alpha comma beta. So if we would have had that subring of a finitely generated ring is also finitely generated, then we would be done. But the issue is there's actually a counterexample, because I can just consider the ring so QXY and consider the subring R XY raised to I. So it turns out that although this will be finitely generated, this will not be finitely generated. Okay, I goes from 0 to infinity. And so to get over this problem, so we need to, so we also have so Z alpha minus beta and Z alpha beta are submodules. So submodules are basically the same concept. So modules, so basically I say, no, okay. So modules of Z alpha comma beta. So what are submodules? Just means that, so M is a subset of N, and M comma N are both are are modules with respect to the same operation. So then, so that means we have, so it's clear that Z alpha minus beta. So the submodules is clear. And now I'll prove a theorem. So essentially, what I'm going to show is that if n is finitely generated on module, and n is a submodule of m, then n is also finitely generated. Um, till what time did I, sorry, till what time did I have? Should I continue, or should I stop here?
I guess I don't know, but like they have a time limit of say 1.5 hours, I guess.
Oh, okay. Okay, I guess I can do
So,
this.
like we can stop the recording.
Okay.
Yes.
Uh, how do I stop it?
Himadri, stop the recording.
Oh, okay. I can